Okay. All right, so we can start. So we were talking last week about the simplex algorithm, right? And basically it's this idea that I start at a vertex of my feasible region, right? I'm trying to solve a linear program. I start at a vertex of my feasible region and I move to a neighboring vertex with better objective value. And then I just repeat until none of my neighbors have a better objective value. And at that point, I declare that I found the optimal point, right? And we were talking about how do we do this? Well, we talked about what's a vertex, what's a neighbor, and how do we make a move to a neighbor? And a vertex was a point that satisfied n constraints with equality and satisfied all the other constraints with inequality. A neighbor is another vertex that shares n-1 constraints in common. Right, 2 points that share n-1 equality constraints, ones that they satisfy with equality in common, are 2 vertices that are a neighbor, and they're kind of like neighboring edge is that one constraint that that they differ on, right? You slide along that. And then we talked about the fact that if you're at the origin, it's easy to figure out whether or not you're optimal. When you're at the origin, you're only optimal if all the coefficients in the cost, the C's, are negative. And to move to a new neighbor, you just increase an X value, like one of your variables, for which the coefficient in the cost function is positive. And you increase that until you hit a new constraint. And then you're at a new vertex with better objective value. And so our idea was once we got to this new vertex, now we're no longer at the origin. And so what we do is we transform coordinates so that we're at the origin in the new coordinate system, and then we repeat the process. And this was what we were writing. And so we end up with, when we do a change of coordinates from the X variables into the Y variables, then we wind up with a new linear program. We're at the origin in this new linear program, like our current point. And then we can again do this check. Are all the coefficients of our new objective function negative? If yes, then we're done. If not, then increase one with a positive, increase a variable with a positive coefficient in the cost and repeat. And so what I was going to do now is go through an example of this procedure. And we'll use this linear program. It's just a simple example for which we can kind of show these steps and how they work. So let me first number the different constraints because we'll be referring to them. So I'll call this one constraint 1, 2, 3, 4, and 5. And then you can see that the origin, it satisfies 2 constraints with equality, right? The point x1 equals 0, x2 equals 0, satisfies constraints 4 and 5 with equality, and it satisfies all the other constraints with inequality. If you just plug in 0, 0 into 1, 2, and 3, you get that the left-hand side is less than or equal to the right-hand side. So the origin which is x1, x2 equals 0, 0, is a feasible point. It satisfies the constraints 4 and 5 with equality. Therefore, 0, 0 is a vertex. So now what do? Our next step is check the coefficients in the cost function and check if they're both negative. If they are, then we're already at a feasible point and it would be optimal because there'd be no way to increase the cost. the coefficients are 2 in front of x1 and 4 in front of x2. Those are both positive. That means we're not optimal, right? So step one now that we're trying to find a better vertex, right? A neighbor that's better. So C1 and C2 are both greater than 0. So move to a new vertex. And to do that, we can increase either x1 or x2. Let's pick one. I'm going to pick x2 because it has a bigger coefficient out in front. So maybe I'll make more gains in my objective value by doing x2, but you could do either one first. So let's pick x2. And now I'm going to increase it until one of the constraints, 1, 2, or 3, becomes active. So which one will become active first as I start increasing x2? And like, where do I have to stop? What's the x2 I get to when one of those constraints becomes active? Yeah, or maybe, sorry, yeah, you go ahead. Yeah. Right, all the x1 stuff is gone because x1 is 0. So really we're just looking at x2 has to be less than or equal to 4. x2 has to be less than or equal to, well, that's a negative in front. So it actually has to be greater than or equal to negative 8/3 or something, which isn't telling you anything. And then the last one says x2 has to be less than or equal to 1. So we increase it until constraint 3 becomes active at x2 equals 1. So can increase x1 until, or sorry, x2, I mean to say, until x2 equals 1. And at that point, we hit constraint 3. So that means we're now at a new vertex. x1, x2. Equals 0, 1. And it satisfies the two constraints with equality. Satisfies 3 and 4, right? So now I do a change of coordinates, right? That was the next step. So I can get back to the origin and do this whole thing again. So my change of coordinates is going to be, I take my two active constraints and I define my variable y to be the right-hand side minus the left-hand side of that constraint. So from constraint 3, or I guess from constraint 4, that one's easier, I get y1 equals x1. And then from constraint 3, I get y1, or sorry, y2 y2 equals 1 plus x1 minus x2. Right, for this one, all I did, this is the right-hand side of constraint 3, and this is minus the left-hand side of constraint 3. So there was a little step I did here. Because actually, if you look at like what happened in this one, if you think, right, just following the definition I said, I take the right-hand side minus the left-hand side. But constraint 4 is written as a greater than or equal to. So first I would write it as a less than or equal to. So it should be written as like negative x1 is less than or equal to. For my definition to work, right? I write it as negative x1 is less than or equal to 0. And then I write y1 is equal to 0 minus negative x1, which just equals x1. Right, because you might think if I did right minus left, I should get y1 equals negative x1 instead. But it was written as a greater than or equal to in 4. Okay. And now what I have to do is I want to do my change of variables in my linear program, right? So my linear program is written in terms of x's, and I want to rewrite it in terms of y's. That means I actually have to solve back out, like with this definition, I need to solve my x's in terms of y. Then I can plug them back into my LP which is in terms of x's, and get a new one in terms of y's, right? So I can also write x1, x2 in terms of y1, y2 as, well, the first one's easy. x1 is equal to y1. And then just rearranging for plugging x1 equals y1 into the equation for y2, and then solving for x2. We get that x2 is equal to 1 plus y1 minus y2. So this was my change of coordinates, and then this is like the definition of my x's in terms of the new coordinates. So my LP then, I'm just going to rewrite the same one. So we get max. My LP was 2x1 plus 4x2, subject to the constraints. X1 plus x2 is less than or equal to 4. 2x1 minus 3x2 is less than or equal to 8. Negative x1 plus x2 is less than or equal to 1. x1 is greater than or equal to 0. x2 is greater than or equal to 0. And now I sub in my expressions for x in terms of y. And my new LP looks like maximize 2y1 plus 4, 1 plus y1 minus y2, subject to the constraints, y1 plus 1 plus y1 minus y2 has to be less than or equal to 4. 2y1, kind of annoying to write, but we get the idea here, I think. Less than or equal to 8. Negative y1 plus, plug in x2 again. And then I have y1 has to be greater than or equal to 0. And my last one is 1 plus y1 minus y2. All right, put it there. Has to be greater than or equal to 0. I made a mistake here. That should be a plus, right? And yeah. So, okay, that was a bunch of writing, but the thing that we got that's kind of interesting, right, is this constraint here, which is this one over here, right? The negative x1 plus x2 is less than or equal to 1. When we plug in the new definition and simplify, that becomes a constraint we're satisfying with equality, right? Because this y1 cancels out with this y1. This 1 cancels out with the 1 on the right-hand side, and we're just getting that y2, negative y2 has to be less than or equal to 0. Or in other words, y2 has to be greater than or equal to 0. So it's going to look like the same LP. You know, we have the constraints. It's an LP defined in terms of y, where we have that y1 and y2 have to be greater than or equal to 0, and then 3 other constraints. And then we have a new objective function, right? And you can see in this new objective function, we get 4 plus, and then some, 6 times y1 minus 4 times y2. That constant 4 is exactly the objective value we had at our old at our vertex. X1 is 0, x2 is 1. And now, like, the new cost function is like, how much can we improve from there? Right. So let me rewrite that one more time, just simplifying everything. So collecting terms. We get maximize 4 plus 6y1 minus 4y2, subject to the constraints 2y1 minus y2 is less than or equal to 3, negative y1 plus 3y2 less than or equal to 11. y2 is greater than or equal to 0. y1 is greater than or equal to 0. And then the last constraint is y2 minus y1 is less than or equal to 1. And so this term right here, that's my objective value at x1, x2 equals 0, 1. And then 6y1 minus 4y2 is my new objective. And so, like, I have in my notation, I had that C tilde is going to be 6 minus 4. So now you say, am I optimal at this vertex? No, because one of the coefficients in that C tilde is positive. That means I can increase the corresponding variable, y1, in order to improve the objective value further. So we see that C tilde 1 is greater than 0. Therefore, increase y1 and repeat. And I think in this case, we hit the first constraint. At y1 equals 3/2. Right, as you've increased the y1, the third constraint never gets violated. This constraint also never gets violated, and this one becomes active when y1 equals 3/2. Now we're at a new vertex. We do one more change of coordinates. We check again, see if we're optimal. And this is how Simplex algorithm is implemented. Like, there's nicer tricks to do some of this stuff, right? So that we don't have to, we're not writing it out by hand, of course, but this is the basic idea behind an implementation of the Simplex algorithm. So it's definitely something that, like, a really nice, clean idea. And then when you go to implement it, it gets a little bit messy because these ideas that are simple geometric ideas are often actually quite challenging to implement in programs, right? I don't know if any of you have ever looked at, for example, computational geometry, like dealing with geometric objects computationally, like taking intersections of polygons or unions, but it always gets very messy very quickly. And making these algorithms also like robust when you have these like geometric operations is quite challenging. So there's a lot of like engineering that goes into making a good linear programming solver, which we're not going to go into, but this gives you the basic idea of how it operates. So I guess I left myself a little bit extra space, which I didn't need. Now there's a few extra issues that we didn't really talk about. One is that the start vertex. So in my example, I just started at the origin and that was feasible. Sometimes the origin won't be feasible. And so I actually have to find a feasible vertex just to get started to do the Simplex algorithm. And the idea to do that is, again, nothing's easy. I start by solving an LP, just a different one, just to find a feasible vertex in the problem I want to solve. So there's a way to make another LP for which the origin is feasible. I solve it. Its solution tells me a vertex of my original LP, just an arbitrary one, just gives me one. Now I can use that to start Simplex algorithm. Complicated, I know, but this is how it works. We also mentioned degeneracy. This was the case where you could find a point that satisfied n+1 constraints with equality. There are ways that you can detect this, and then they slightly perturb the right-hand side coefficients to break the degeneracy. So like, for example, if you had in the plane, if you had 3 lines that pass through a point, you slightly perturb the right-hand side of the equation that defines those planes, and it pushes them apart. So only 2 intersect at a point now. And then you solve that problem. And since this perturbation was small, it doesn't affect the end solution. One other thing is that if the LP is unbounded, you end up getting to, there's a way to detect it. I won't go into the details, but you get n constraints with an infinite number of solutions. Like you get down to a linear set of equations with infinite number of solutions. And at that point, you can declare that your LP is unbounded. But this is an additional check that has to be done. The other question, of course, is what, yeah? That's a good question. So the question was just, if the origin isn't feasible for the primal, then will it be feasible for the dual? I don't know that you can necessarily say that. But I think, I'm trying to remember, I actually don't remember exactly how you find this other LP, but I think it actually has to do with the dual, this alternate LP that you solve to find the starting vertex. But I haven't looked at that in some time, so I don't remember exactly how it works. So the runtime of this, like if you think in the absolute worst case, maybe I could bounce around and visit every single vertex of the feasible space before I find the optimal one. And so then you can ask the question, how many vertices are there in the feasible space? And this can be large. So all you can really do by saying, in the worst, it never visits a vertex twice. So in the worst case, it visits all of them. So then the number of vertices visited, oops, is less than or equal to n plus m choose n, where this is number of variables, this is number of inequality constraints, and the n in the denominator is the number of inequality constraints. And so this is exponential, actually, right? N choose, you know, like if you take n choose 2, it looks something like n squared. N choose 3, as long as n is big, looks something like n cubed. You know, it's a complicated expression, but so this is, if m is significantly larger than n, then this will look like something that's exponential in n. So this is exponential in worst case. But in practice, it runs fast. So this is an example where people still use it. So in practice, you visit nowhere near all of the vertices in the feasible space. However, there's an example, like someone has constructed an example that shows that, you know, there exists a feasible space for which the simplex algorithm will visit an exponential number of vertices, meaning its worst case runtime truly is exponential. However, just give it a random LP and it won't do that typically, like, so it runs fast. But this then made an interesting, like there was an interesting line of work. These linear programs are really useful. There's a good algorithm out there, simplex algorithm. It seems to run really well. And then there was this question, like, is it actually a polynomial time algorithm? Then someone came up with a counterexample to say, no, it's not. Here's a crazy feasible space for which simplex will visit an exponential number of vertices. And so then there was like this question, is linear programming even efficiently solvable? Or is it one of these hard problems? And then there came up with this person invented something called interior point methods, which have a guaranteed polynomial runtime. And interior point methods, the name really gives you a lot of information about how it works. Rather than trying to hop around on the vertices, I start in the interior of the feasible space, and I try and kind of follow a gradient of my cost function out to a vertex, right? Start in the middle and then like descend or ascend my cost until I hit a vertex. This has to operate in iterations, and you know it's kind of complicated. There's step size choices, all this stuff. You know, it's not simple, but this was the algorithm, and it can be proven to run in polynomial time, thus showing that linear programming is an efficiently solvable problem. That being said, still for many problems, simplex actually runs faster than the interior point methods. So typically, if you have a linear programming solver, it will contain both interior point methods and simplex method. And then you can kind of choose with a flag. Like if you've looked at question 4 on the assignment, it has an option to use both. And I think the way I've written it, like in the assignment, the PI file, like it uses a simplex method as the default. So. But anyway, so interior point methods have polynomial runtime. The true expression is a little bit complicated, but this gives you the idea. But in practice, simplex method is often faster. So that's, I think, all I wanted to say on linear programming. Just to give you a few, like, maybe just the takeaways that I hope you get from this section are, so the details of how to solve simplex algorithm or how simplex algorithm works, it's interesting, but that's not really like what I'm trying to get at. Like the thing that I hope for you to understand is like, what is a linear program, right? Like, what do they look like? How could you take a kind of one of these word problems like product 1 and product 2 and so on and turn it into an objective and some constraints? How do we convert that into a standard form so that you can input it to a solver, right? Like the one in the assignment question. What's the dual, because this is an important concept, this idea of duality. And those are sort of the main ideas, right? I mean, I wanted to give you some insight into the simplex algorithm so it doesn't just feel like a black box that you have no idea what's going on. But don't feel like your objective in studying or something is to memorize the operations of linear or of the simplex algorithm, right? That's not really what I'm trying to get at. So anyway, why don't we take a 5-minute break and then we'll move to the second last section of the course, which is NP completeness. So let's now get into this kind of large chapter, which is NP complete problems. So I don't know, have people heard these phrases like P versus NP, or the problem like, does P equal NP? Like, is there a show of hands if you have heard this? Okay, some people. Actually, if you drive along, I don't know if you probably don't know, but there's a road in Kitchener called Glasgow, which runs like east-west. And there's a house on like the south side of the street, and it has like a rock in the front yard. And on it, it must be a computer science professor that lives there, that there's like a carving that says something like co-NP not equal to P or something like this. I forget even what the statement is. But anyway, it's like, if you drive by there, you should look for a rock on the south side of a driveway. But anyway, these questions about complexity classes are like kind of fundamental to algorithms, right? And I think one of the biggest, or maybe the biggest open problem in computer science is just this question of whether P equals NP. And so you may have heard this. We're going to try and understand exactly what that question is asking, what it means, how we go about talking about these complexity classes, what problems lie in them, things like that. So for this, we've talked about designing efficient algorithms, right? And we've designed efficient algorithms for shortest paths, minimum spanning tree. In dynamic programming, we did longest increasing subsequence. And so this word efficient, what do we mean by it more precisely? Like, what's an efficient algorithm? When we talk about complexity theory, it takes on a very coarse meaning. So first of all, if we have a problem, its input size is the number of bits that we need to represent that input. So for a graph, right, you have to input its vertex set, its edge set, and then its edge lengths if you want. So you could say, it would be the number of bits, like log v or something would be the, you have to do v different vertices. So it's going to be v plus e, and then log of the number of the maximum value you have to assign to the edges. So maybe like, edge weights are 32-bit integers or something. So that ends up being like just a constant times v plus e to input a graph. But in any case, we have this input size, right? So again, if you have an array of length n and each entry is constant number of bits, then that's an n bit. It takes only order n bits to represent the input. And so an algorithm is called efficient if its runtime is bounded by a polynomial function of the size of the input. So when we write the input as n, we would say an algorithm that runs in n squared time is efficient. We'd also say one that runs in n to the 10 time is efficient in this section right now, like when we're talking right now. But if the best algorithm we can find runs in 2 to the power of n time, that is not considered an efficient algorithm. And so even with this coarse definition of efficiency, there are many problems for which we do not have an efficient algorithm. Two that we've talked about in some detail are factoring and also knapsack. If you remember, knapsack ran in n times 2 to the power of m time, where our input was only n plus m or something like that. So in these cases, the best known algorithm runs in exponential time relative to its input size. Now, when we start talking about complexity theory, we're only going to be talking about what are called search problems. So I first have to tell you what a search problem is. they're essentially, rather than problems where we're trying to minimize or maximize something, they're just problems where we're trying to decide either yes or no. Our output will always be either a yes or a no. And if our output's a yes, then I have to be able to convince you it is yes. So we'll get into this in more detail, but that's what a search problem means, as opposed to like the types of problems we've been talking about. The kind of classic example is satisfiability. So if you remember, we talked about Horn formulas already, but I'm going to go into satisfiability. It has a lot of the same structure as Horn formulas did. So we have, in satisfiability, we have Boolean variables. They take on the value true or false. And they can represent things like you have X represents the statement, it is sunny outside. And that is either true or false, right? And then you can also talk about, I don't know, something else, Y. I'll say, I'm not really giving an assignment, right? Because the assignment is true or false. So X represents, I'm going to use these 3 equal signs, is equivalent to the statement of, I don't know, it is warm outside. Doesn't have to be about outside in temperature. And then a literal, as we talked about before, is either a variable X or its negation. So you can have X with a bar on top is the negation of X. And so then it's read as the statement not, it is sunny outside. Which in English, we bring the not inside and we write it is not sunny outside. Right, so if X is true, then not X is false. And then we have these 2 operators, which are called and or conjunction, and the or operator, which is called disjunction. So the and operator, we can say X and not Y. And so that would be, it is sunny and not warm. Right? If that evaluates to true, then that would be the statement. And then the other main operator is disjunction, which is an or. And so you could write X or Y or not Z, let's say. Or here, how about I write just a simpler one? X or Y is, it is sunny or it is warm. And then in satisfiability, a clause is a disjunction of literals. So it's a bunch of literals, that's the variable or its negation, with ors in between it. So that's a clause, right? That has 2 literals, the X, the 2 positive literals there, and then 1 or connecting them. Another X or not Y, that would be a clause. X or Y or not Z or I don't know, W, that's another clause. Anything like that. And then a Boolean formula can be defined in different ways, but there's a kind of standard form, like what we had with linear programs, for Boolean formulas as well. And it's called conjunctive normal form. So in conjunctive normal form, you have clauses, which clauses have only ors in them. And you connect clauses together with ands. So it's a conjunction of clauses. And each clause is a disjunction of literals, an or of literals. So a Boolean formula is in conjunctive normal form if it is a conjunction of clauses. And just by definition, each clause is a disjunction of literals. So you could write it as X, let's say X or Y or not Z, that's one clause, and X or not Y, and right, that would be an example. That's clause 1, clause 2, that's an and those are ors. And then the goal of the satisfiability problem is to find a satisfying truth assignment. So that's an assignment of true or false to each variable so that the overall formula evaluates to true. Now, the nice thing about this conjunctive normal form is what it means to have a satisfying truth assignment can be said more simply than just saying the overall formula evaluates to true. How do I get this clause to evaluate to true? The clause just, what it's saying is X has to be true, or Y has to be true, or not Z has to be true. So to satisfy this clause, I have to set one of its literals to true. I can do it by setting X to true, by setting Y to true, or by setting Z to false. Any of those would work. Or multiple, right? I could set, because with an or, I mean, I just have to have at least one of them has to be true. And then I have an and between clauses. So that means I have to do that for every clause. So a satisfying truth assignment is an assignment of true or false to each variable so that every clause contains a literal that is true. That's the right. So let's just do two examples. Let's say I have, oops, X or Y or not Z, and X or not Y. And then I ask the question, is there a satisfying truth assignment? Is there a satisfying truth assignment? So can you find one? Can I assign true or false to X, Y, and Z such that each clause contains a true literal? Can someone give me an example? Yeah. Yeah, perfect, right? Because X appears as a positive literal in both clauses. So setting it to true, I'm done, actually. I can do anything I want with Y and Z. So yes, take X equals true and anything for Y and Z, right? Set them to true or false. Let me give you another example. I think we get it, but I just want to make sure because it's kind of, if you haven't seen this before, it's definitely notation heavy, right? And not that friendly to read. So let's say I have X or Y or Z and X or not Y and Z or not X and Y or not Z. and not X or not Y or not Z. Okay, it's long, but it's actually kind of an interesting one. So let's look at the first and the last clause, right? Just to start, yeah?
Is it technically not satisfiable?
Yeah. No, I think you're thinking along the right lines. So let's just look at it quickly. So the first clause tells us one of these variables has to be set to true, right? So I got to set X, Y, or Z to true for sure. And the last one tells me I have to keep one false because not X or not Y or not Z has to be true. So now let's set X to true. That satisfies this one, right? But now this is false, so I have to set Z to true, right? But now in this clause, not Z is false, so now I have to set Y to true. So setting X to true forced me to set both Y and Z to true, which then violates the last clause. And if I do it with Y, I get the exact same thing. If I set, let's say, okay, let's not set X to true then, and let's instead do Y. If I set Y to true, this one forces me to set X to true. And this one then forces me to set Z to true to satisfy those clauses. And then I violate the last one. So as soon as I set one to true, these intermediate three clauses force me to set all the other two to true as well, meaning I can't satisfy the last clause. So this cannot be satisfied. There's no assignment of the variables that satisfies all the clauses. So there's no way to satisfy both the first and last clause. Therefore, no satisfying truth assignment. Oops. Okay, so this is a search problem. Because think about what I'm doing. I'm just going to answer yes or no. I'm going to say yes, there's a satisfying truth assignment, or no, there is not. Right? The first one had an answer of yes, the second one had an answer of no. And so this is the problem that is called SAT, or satisfiability, and it's an example of a search problem. One thing that's interesting about SAT is that there's no known efficient solution for it. But it's also kind of has this neat transition from being easy to hard in that the problem called 2SAT, where each clause only has two variables in it. So neither of these examples would satisfy it. But if each clause only contains two variables, then we can solve the problem efficiently. You can actually encode the formula as a graph in that case, and there's a nice way to solve it as a graph problem. However, if you allow each clause to contain three literals, the problem is hard, and there's no known efficient solution for it. So if we limit them all to two, we can solve it. If we let them have three, it's hard. And of course, if you let them have four or more, then it's can't get any easier. So 2SAT solved efficiently, 3SAT hard to solve. And 3SAT is just as hard as SAT, it turns out, where I allow there to be as many literals as you want in each clause. So this leads into our definition of a search problem. And it's just a problem that takes the following form. You're given a problem instance I, and you want to find a solution S, find a satisfying truth assignment, or determine that no solution exists. So find a solution is like answering yes, or determine that no such solution exists is like my no. So for SAT, the instance I is the Boolean formula. Let's say in conjunctive normal form. And the solution S is a satisfying truth assignment. Now, we want to restrict the class of search problems we're considering a little bit to be what we call well-defined or well-posed search problems. And those are the ones where it's kind of a sanity check or something, but not all problems satisfy this. It's where if you claim you have a solution, I can verify that it is a solution. So let's take SAT as an example. If you tell me you found a satisfying truth assignment, I can check efficiently that it is or is not a satisfying truth assignment. That kind of makes sense that, like, intuitively speaking, that that's something we might want. Because if we can't even verify that a candidate solution is a solution, then it's sort of hard to talk about the problem, right? You don't even know if you've got a solution. So we say that a problem is well defined if two things are satisfied. One is that the solution isn't too long. So the solution has a size that's bounded by a polynomial in the input size n. So you can't like your problem can't ask you to output a solution that's exponential in the size of the input. And the second is that there's a polynomial time algorithm that takes as input the instance and the solution and determines whether or not S is a solution to I. So polynomial time algorithm that determines whether or not S is a solution to I. So are these satisfied for SAT? Or can you see why they're satisfied for SAT, these two criteria? The input's a formula, right? So presumably the formula contains all the variables because, I mean, you only have to consider the variables that appear in the formula, right? So our satisfying truth assignment is just going to be like an array of length equal to the number of variables with either true or false in each entry. That's actually going to be linear in the input size, right? The formula might be longer than the number of variables. And then if you claim you have a solution, I can check it quite efficiently because all I do is I just go through clause by clause and I check, is a literal in the first clause true? Yes or no? Is a literal in the second clause true? Yes or no? And so on, step through the clauses. So again, I can verify it actually in linear time in the length of the formula in the case of SAT. So one solution is just true, false. Assignment for each variable. Which is linear in input size. And then 2, to check solution just check each clause has a positive literal. And so in the literature, these, rather than search problems, people often call these decision problems. It's just the same thing, just with a different name. And the word decision comes from the fact that you either output yes, meaning solution exists, or no. Right? And then basically a search problem, another way to think of it, right, is it's this yes, no problem, where if you claim yes, you have to be able to prove it to me. And so you have to be able to hand me the solution, and I can actually do a little bit of work, a polynomial amount of work, and determine that yes, you found a solution, or no, you haven't. Okay. So now what I'm going to do is go through a few different problems that are search problems and just introduce them to you. I also want to convince you of this kind of interesting line that seems to exist between problems that look pretty similar, but one of them can be solved efficiently and the other one cannot. So one example we already saw is 3-sat versus 2-sat. But there's some other kind of interesting barriers or something between what's hard and what's easy, where they don't feel too far apart from one another. So traveling salesman problem, or TSP. So we can phrase this problem in two ways. One is as an optimization problem, which is probably the one that you're the most familiar with, if you've seen this problem before, and the other is a search problem. So for both problems, we take it as an input, an undirected graph G with edge lengths. And the only important thing is that the graph is complete, meaning that there is an edge between every pair of vertices. So for example, on 4 vertices, the graph will look like this. Right? It has all the edges in it with some weights on it. 1, 2, 3, 8, 4, 7, something like that. I don't know. And then the optimization problem is find a tour or a cycle in the graph that visits each vertex exactly once and has minimum length. I don't even know in this picture I just drew, what's the solution? I just made it up. I mean, you can go around the outside, right? And then you get 11, 14. But can you do better than that? Right, like I'm just saying, like, go like this. Like as a bow tie, does it do better? No, right? Yeah, there's kind of 2 bow ties, right? That the vertical one, right? Like I could go 1, 3, 4, 8, but that's not better. I could go 2, 3, 7, 8. That's definitely not better because I get both the 8 and the 7. I think it might be going around the outside. But anyway, it's even hard to see, right? I've only got 4 vertices and we're already struggling a little bit. And so this is an interesting problem. Like, okay, already, let me say to you, I claim the optimal solution has a length of, what did I say? 15, actually, right? 8 and 6, 14. The optimal solution has a length of 14. How do you verify that? Like, what if I'm lying to you? The only way you can really verify that is to try and solve it yourself. So this is not a search problem, this optimization problem, right? It's like find a solution or determine no solution exists. A solution always exists in this case because it's just find the shortest tour. But it's not easy to check. Like, I could be lying to you. And maybe someone, did you find a better tour or no? No, okay. I thought maybe you were. But anyway, I think maybe it is just 14, but whatever, right? Like, that's the point. So, yes? No, in this version, it has to be a closed tour, start and end at the same place. But there is a variant where instead, either the endpoint is free and you can just be a path, or where you're given the start and you're given the end vertex, and now you want to find the shortest path that visits every vertex on its way. So, but this is the motivation for instead talking about a search version of this problem, which is where I give you a budget and I ask, can you find a tour, right, that visits each vertex exactly once and has a length less than or equal to my budget? And do you see why that's different? Like now, if I claim I found a solution, you can verify it. So let's take that picture I drew up there and say I give a budget of 15. And now I claim I found a solution, right? And I say, okay, just go along the box, like the outer part, right? It gives me a cost of 14. Now you can verify, right? You just add up the edge lengths on the tour and check that it's less than the budget. So given this version is the whole thing is you have a budget and you want to know if it has a length, if you can find a tour that has a length less than or equal to that budget. And so when we're talking about complexity, we're only really going to be thinking about search problems, well-defined search problems. It's important to know that this search version, even though it might be less natural, it's still like is kind of equivalent difficulty to the original one. And so we'll talk about this more later, but the two versions reduce to one another. So suppose we have an algorithm for, let me call it TSP opt, the optimization version. Then definitely you can use that to solve the search version. Right? If you're given an instance of the search version of the problem, you're given a budget and a graph, just take your magical optimal TSP solver, find the minimum length tour, and then just, if it's less than the budget, output it as your solution. If it's greater than the budget, say no solution exists. So the steps would just be find optimal tour. If it is within the budget, oops, budget B, then return it. Else, return no solution exists. And then now the other question is, solve how do you solve TSP opt given an alg for search version? And this is actually the last question on the assignment, if you've taken a look at it. So here, right, you're given a budget, you're given a magical algorithm, right? That if you give it a TSP graph and a budget, it can tell you whether there's a solution or not. Like whether there's a tour that satisfies that budget. And now you want to use that, call it multiple times to find the optimal TSP. So if you knew the length of the optimal TSP, you just input that as your budget and then call your search solver, right? And it would give you the tour. The only problem is you don't know the budget. So you have to search over the budget, right? And the only thing is just make sure you search efficiently over the budget. Right? We know how to kind of not exhaustively search a range, but search in a more intelligent manner. So that's all I'll say. That's the only thing. And then you can make it takes at most a polynomial number of calls to your search solver to solve the optimization problem. And then the other thing, which I already kind of said in words, is why isn't the optimization problem a search problem? It's exactly because I don't have, as far as I know, sorry, let me go back up to here. We needed number 2 to be satisfied. There is a polynomial time algorithm that takes as input the graph in this case and the tour and determines whether or not it is an optimal solution. But in the case of TSP, right, that would be just as hard as solving TSP. And so the reason that we don't think this is a search problem is how do you efficiently check that a solution is optimal? And we don't know of an efficient way because TSP, as far as we know, is a hard problem. Both the search version and the optimization version are hard problems. So tomorrow, I'll give you an example of a very related problem that's actually easy. And then we'll do a few more examples. Okay, thanks everyone.